Can you imagine? Scientists have finally captured the true appearance of free atoms with high-definition cameras. It wasn't that long ago. The MIT team has directly imaged free atoms in spacetime for the first time. Not only did the quantum phenomenon of bosons and Bose-Einstein condensates be clearly observed, we also catch fermions in reverse, and the whole process of them forming pairing in the back PCS intersection region. This breakthrough relies on a brand new atomic resolution microscope, capturing atomic clouds through a relaxed landscape, instantaneously turn on the optical lattice freezing motion. The image was imaged by fluorescence or Raman sideband cooling. Scientists have finally achieved the direct verification of the century-old foundation of quantum mechanics, de Broglie waves, and the properties of quantum statistics. It opens up a new path for real-time visualization of strongly correlated quantum gases. Why are free atoms so difficult to observe directly? This begins with the fundamental principles of quantum mechanics. The Heisenberg uncertainty principle tells us the position and momentum of microscopic particles cannot be precisely determined simultaneously. For a single atom to measure its trajectory, it will inevitably exert external force on it, change its state of motion, and if you want to measure its momentum, you have to avoid strong interference. However, its exact location cannot be determined. Atomic imaging technology of the past, absorption imaging, only the overall shadow of the atomic cloud can be photographed. It is impossible to distinguish the behavior of individual particles. Scientists have always hoped to let atoms roam freely. It retains its intrinsic quantum state. At the same time, they can be fixed in their positions in a very short time, achieve single atom level visualization. Only in this way, to directly observe de Broglie waves and quantum statistical effects. Verify a century-old theory. The so-called free atom, it refers to not being bound by a deep well. It can be in continuous space, interacting groups of ultra-cold atoms. Unlike the deep optical lattice or magnetic trap binding common in previous experiments, free atoms retain more freedom of thermal motion under weak binding. It appears to be closer to the ideal gas. In this state, quantum correlations between atoms and thermal fluctuations can be depicted more realistically. The first breakthrough in space-time imaging of free atoms not only allows for the visual capture of the wave characteristics of particles, it can also reveal the quenching of bosons and Bose-Einstein condensates, and the anti-quenching and pairing behavior of fermions. This is a milestone in the verification of de Broglie waves and quantum statistics. Review the theoretical basis. In 1924, the French physicist Louis de Broglie proposed the wave hypothesis of particles. All microscopic matter particles have wave-particle duality. From then on, quantum mechanics is based on a probabilistic interpretation of the wave function C. De Broglie waves become the intuitive source of the reality of the wave function. For a single atom, the distribution of its wave function in space will form interference and diffraction effects. But because the particles are too small, traditional optical means are difficult to image directly. Boson-Einstein statistics apply to bosons with integer spin, allowing multiple particles to occupy the same quantum state, expressed as a clustering effect. And Fermi-Dirac statistics apply to fermions with half-integer spin. Following the Pauli exclusion principle, it is manifested as anti-clustering effect. These two kinds of statistical behaviors are clearly reflected in macroscopic condensed matter, but it's more subtle in a freely moving atomic gas. Direct verification by high-resolution experiments is required. And here's the really exciting part. The scientists also observed pairing in the back BC's crossover region. Bose-Einstein condensation and Cooper's theory of superconductivity in physics. It looks different. The former are tightly bound Bose pairs. The latter is a loose Cooper pair in the band. The back PC's cross region is the smooth transition region of the two. Here you can adjust the strength of the interactions between atoms. Achieve controlled conversion from tight-bound pairs to loose pairs. Using free atom imaging, researchers can directly measure the diatomic correlation function, obtain information on pairing size and contact parameters. It provides the first time-space evidence for verifying the theoretical model of many-body quantum systems. So, how did the MIT team achieve this quantum world live broadcast? First, they used weak light wells to relax and trap ultra-cold clouds of atoms. Maintain a shallow enough depth of view. Give atoms limited freedom to swim in the well. It will not lose its original thermal fluctuation characteristics due to excessive binding. Afterwards, the atoms are transferred to a weakly bound infrared light field. Complete the natural manifestation of interactions and quantum statistical effects in millisecond scale-free evolution. Next, the experimental team will wait for the atomic cloud to evolve freely for a predetermined time. Immediately turn on 3D optics, Ginger. The periodic vision formed by laser interference is instantaneously turned on. They freeze atoms in different positions in their respective optical slots. The switching time of this process is extremely critical. It is usually completed in microseconds or even less. avoid significant atomic diffusion during the establishment of the laser field. Therefore, the original information is lost. After the atoms are fixed by the optical lattice, the researchers use excited atomic fluorescence imaging. The position of individual atoms is determined by collecting the fluorescent photons emitted in each optical slot. For the sodium atom, direct excitation and collection of fluorescence by atomic transition lines, and for lithium atoms, then combined with Raman sideband cooling technology, while maintaining the atomic position unchanged during the cooling process, reduce image blur caused by thermal fluctuations. The final imaging resolution reaches the submicron level, capable of continuously imaging the same atomic cloud multiple times. The acquired single-atom fluorescence images still need to go through complex data processing. It includes background photon removal points, diffusion function, and subpixel localization of atomic checkpoints. Researchers have developed automated image processing algorithms. By combining Gaussian fitting with most natural estimates, extract precisely the two-dimensional position coordinates of each atom. On this basis, further calculate the two-particle correlation function. The atomic spacing distribution and quantum statistical effects are revealed. By analyzing the remote correlation function, it can also extract the paired wind and short-range contact strength. To obtain pairing size and interaction information, this data processing process provides high-precision experimental evidence for subsequent theoretical model verification and quantum many-body simulation. The experimental results are encouraging. In the boson-steam condensate experiment of the sodium atom, the researchers captured instantaneous images of a large number of bosons in the same quantum state. By analyzing single-atom imaging data, the team plotted the decay curve of the two-particle correlation function with distance. Observed that the associated wind is obvious at zero distance, and as distance increases, the effect quickly diminished. This phenomenon is related to theoretical simulations are highly consistent. The wave nature of de Broglie wave and the formation mechanism of macroscopic quantum coherence in both condensation are shown intuitively. Previously, only circumstantial evidence supported boson clustering. This time-space visual imaging achieved the first direct verification of the century-old theory. For atomic gases with spin-semi experiments reveal the anti-clustering characteristics of fermions due to the Pauli exclusion principle, with single-atom localization. The team also directly observed the process of pairing fermions in two spin states under moderate interaction. In the back PCS area, as the interaction transitions from strong to weak, the pairing pattern gradually evolved from tight Persian pairs to loose Cooper pairs. It's visible on the image. When the interaction zone is weak, the pairing size increases rapidly. This change is quantitatively extracted by remotely correlating the width and height of the wind. It provides a visual reference for understanding the macroscopic logistics and coherence of Cooper pairs in soup. We go one step further. The team took advantage of the long-range decay behavior of the two-particle correlation function, combined with theoretical models. The typical spatial scale of paired pairs is obtained. At the same time, the contact parameters were directly measured by the correlation function, strength of the short-range limit. The strong correlation of diatoms over short distances is characterized. These two vectors are directly related to the superfluid coherence length and critical temperature of many-body quantum systems. It has important guiding significance for high-temperature, superconducting quantum simulation, and the study of quantum materials. In previous experiments, such parameters can only be inferred indirectly by momentum-resolved techniques or spectroscopic measurements. This in situ imaging provides the first direct measurement solution without waste-liquid transformation. In addition, the researchees also use the relationship between atomic number density fluctuations and thermodynamic responses. In situ temperature measurement is achieved through detailed statistics of atomic number variance in different regions, and combined with the compression coefficient of the system. The team was able to directly derive the local temperature distribution of the gas without disrupting the atomic cloud. This technology compensates for the limitations of traditional time-of-flight imaging, which can only give the overall average temperature. Make future studies of non-equilibrium quantum dynamics, thermalization processes, and many-body localization. More local thermodynamic information can be obtained. Since Louis C. Blow intended to propose the Polynesian binomial in 1924, direct experimental evidence of particle volatility has always been a core pursuit in the field of quantum mechanics. This in situ imaging experiment is the first time to directly observe the de Broglie wave effect and its induced quantum statistical behavior in space. It provides the most intuitive empirical evidence for the basic principles, including Persian-Einstein condensation and fermion pairing. In the past, scientists could only verify this indirectly through momentum resolution or interference experiments. Single-atom imaging moves the verification path from momentum space back to real space. The visualization of fundamental research in quantum mechanics has been greatly improved. As Richard Feynman said, if you think you understand quantum mechanics, then you must not understand quantum mechanics. The beauty of science lies in constantly challenging the limits of our imagination.